Next section, 7.4, we are going to use boundary conditions to find a particular solution, and it will be the complete particular solution, because a particular integral is one of the solutions. So you could actually have a particular integral which is one of the solutions. Right, so over here we have got an example of a differential equation, and boundary conditions is the set of information, sufficient set of information that you can substitute into our equation to help us identify those constants that we normally get, like a and b, in our general solution. If it's a simple differential equation of order 1, we just need coordinates of a point. So it fixes the general solution to a particular spot, and then you've got the particular solution. In differential equations of order 2, we need to have a point, so information about the point, and also what the first derivative is at that particular point. So you need to have 3 pieces of information. Okay, so let's start by looking for the complementary function. So we're going to look at this left-hand side. So it's m squared minus 1 is equal to 0. That gives me m minus 1, m plus 1 being the solutions. Now, therefore, the complementary function must be y equals to a e to the power of 1x plus b e to the power minus x. We're going to look for the particular integral. Now, the particular integral here, you would let y equals k e to the power of x. But because you have got e to the power of x being part of the general complementary function, then we're going to try kx e to the power of x. So let's differentiate it once. So that's going to be u, and that's v. So it's going to be k e to the power of x. Plus, we're going to leave it as kx, and then multiplied by a to the power of x differentiated, which is the same. The second step is differentiated the first derivative. So that's already k e x. I've already differentiated it because it's exactly the same as our function y. So it's 2k e to the power of x plus kx e to the power of x. So substituting into the equation, which is in y double dash minus y equals to 2e to the power of x. So to get 2k e to the power of x plus kx e to the power of x minus kx e to the power of x, and on the right hand side is 2e to the power of x. So that's the bit we want to cancel, and it cancels. So we've got 2k is equal to 2, giving us k is equal to 1. So the general solution will take the following form: a e to the power of x plus b e to the power of minus x, and then we have 1 lot of the particular integral, so 1 times x e to the power of x. So now, how do we use the boundary conditions? Y dash is 0 at the point with the x coordinate equals 0, y equals 0. So the first step is substitute x equals 0, y equals 0 into the general solution. So we have 0 is equal to a e to the power of 0, so a b e to the power of 0 plus 0. So a plus b is equal to 0. So I can't find a or b, but I know that when you add them together, I get 0. Then, second step is to differentiate the general solution. So y dash is going to be equal to a e to the power of x minus b e to the power of minus x, and then we've got x goes to 1 times e to the power of x plus x times e to the power of x. And then we're going to substitute the y dash being equal to 0 at the point when x is equal to 0. So 0 is equal to a times 1 minus b times 1 plus 1, and here that will go plus 0. So the second equation is a minus b is equal to minus 1. So we have got two mini equations, this one and this one. So from this one, we've got a is equal to minus b. Let's substitute it into that. That gives me minus b. Minus b is equal to minus 1. So that gives me b is a half. So a must be equal to minus a half. So the particular solution is y equals a is minus a half, so it's minus a half e to the power of x. B is a half plus b a half e to the power of minus x, and the particular integral was x e to the power of x. And this is the particular solution, so no more family of solutions. Okay, so example 16, we have got x double dash plus x is equal to 3 sine 2t. And we are told that a particular integral has the following form. So they are already giving you the particular integral. If that happens, this is normally for a reason, to make it a little bit easier for you, so you don't search for the particular integral. You know, it makes your life a lot easier. So there you go. So I've differentiated these. Let's actually find the value of lambda here. So substituting it into the actual equation, we are going to obtain the value of lambda. So make sure that you're working with the variables that are provided. It's so easy to go back to x's and y's, which you could do. However, you would need to clearly explain that you're going to temporarily let your x being equal to y and t being equal to x, and then revert back in the final solution to the correct variables. So 3 lambda is equal to 3. Lambda is equal to minus 1. So the particular integral for this question is x is equal to minus sine 2t. Okay, for the complementary function, we are considering m squared plus 1 equals 0 as the auxiliary equation. So x, it's going to be m squared is equal to minus 1, so m is equal to plus or minus I. Okay, so the real part, remember the solution to the, when the complex numbers are solutions to the auxiliary equations, would be x is equal to, and here you would have e to the power of real part of the root, so alpha t, and then you've got, let's say, a cos beta, when that's imaginary part, plus b sine beta t. That would be the solution to the homogeneous equation. So in our case, x equals, now the real part is 0, so you are going to have that as e to the power of 0t, which will become 1. And then you've got a cos 1t, so t, plus b sine t. So the complementary function of the general solution is a cos t plus b sine t. So what's the general solution? We've got to state it. It's x's, you see, it's so easy to put x is equal to complementary function plus particular integral. So x equals to a cos t add b sine t, and then minus sine 2t. So remember, now they are giving us some boundary conditions. Let me just double check. X is equal to 0, x dash is equal to 1, t is equal to 0. So we're going to fix our curve. So remember, this family of curves, there's infinite number of curves, but we are going to make it pass through the origin. and the gradient at the origin is equal to 1. First thing is to put x equals 0, t equals 0. So what we can substitute here, so it's going to give me a cos 0, which is 1, plus b sine 0, which is 0, minus sine 2 times 0, which is 0. So we have a 0 is equal to a times 1 plus 0, so a is equal to 0. Okay, so we're going to differentiate it. Now I'm actually going to leave that a for now, but I could just substitute it straight away, but that's okay. There you go. So we're going to put t is equal to 0 and x dash is equal to 1. So minus a times sine 0, but a was already 0, plus b times cos 0 minus 2 times cos 0, because 2 times 0 is 0. So that is equal to 0. This is b times 1, so it's b, and that's minus 2. So it's 1 is equal to 0 plus b minus 2, giving me b is equal to 3. So the particular solution is going to be the complementary function, which is a cos t. A was equal to 0, so don't have that. B sine t, so it's 3 sine t, plus the particular integral, which is minus sine 2t. Okay, so you are done with this section, so you can have a go at exercise 7D.